In this video, we will walk through the solutions for the second homework assignment. The first question over here is asking us to show that n factorial is little o of n to the power n. By definition of little o, we essentially need to show that limit as n tends to infinity, n factorial divided by n to the power n tends to 0. So let's try to prove that over here. N factorial divided by n to the power n is basically n factorial can be written as n into n minus 1 multiplied by n minus 2 and so on up to 1, and n to the power n is basically n into n so on into up to n times basically. So if we divide these terms, basically if we factor out these terms in the numerator and the denominator, this expression becomes n divided by n multiplied by n minus 1 divided by n multiplied by n minus 2 divided by n and so on up to 1 divided by n. So notice that each of these terms, right, these terms, they are less than equal to 1, and this last term, as n tends to infinity, 1 by n is actually 0, right? So essentially this expression is in this expression we have some number less than equal to 1 multiplied by 0, which is basically equal to 0, and therefore limit n tends to infinity, n factorial divided by n to the power n is equal to 0. This basically proves that n factorial is in fact little o of n to the power n. In this question, we have to figure out the relationship, the asymptotic relationship between the functions given under column A and functions given under column B. Essentially, we need to figure out whether the functions given under column A are big O or little omega or big omega or theta of the functions given under column B. So let's start from the first row over here. So notice that any polylogarithmic function is always a little o of a polynomial function, right? So this n to the power epsilon, this is a polynomial function, for example n square, n cube and so forth. So given this standard result, this log to the power k of n is going to be a little o of n to the power epsilon. As it is little o, it has to be big O. Now as it is little o and big O, it cannot be big omega, it cannot be little omega, and it cannot be theta, because to be theta the function has to be both big O and big omega of a function. So essentially log to the power k of n is little o of n to the power epsilon. The second row over here we have n to the power k compared to c to the power n. So notice that n to the power k is a polynomial function, right? Basically think of this as n square, right? And c to the power n, this is an exponential function, for example 2 to the power n. Now obviously any exponential function will grow much faster than a polynomial function. Now notice this is especially true because c is greater than 1, okay, and therefore basically n square or n to the power k is going to be little o of c to the power n. So this is little o, and as it is little o, it has to be big O. Now as it is big O and little o, it cannot be big omega, it cannot be little omega, and it cannot be theta. Okay, the third question here is comparing 2 to the power n with 2 to the power n by 2. Now among all of these questions, perhaps this is the only one for which you really need to compute the limit. So let's compare 2 to the power n by 2 to 2 to the power n. So let's compute this limit n tends to infinity, 2 to the power n by 2 divided by 2 to the power n, right? So this basically will become limit n tends to infinity. So let's do the subtraction. This will basically become 1 upon 2, subtraction of the exponents I mean. So this will become 1 upon 2 to the power n by 2. Now as n tends to infinity, this will tend to 0. Okay, so basically what this means is 2 to the power n by 2 all right, let's write it the other way, right? So basically 2 to the power n is little omega of 2 to the power n by 2. Okay, so that's what is shown here. So this is going to be little omega, and because it is little omega, it has to be a big omega as well. Now because it is little omega and big omega, it cannot be big O, it cannot be little o, and obviously it cannot be theta. Okay, the fourth question here is comparing n to the power log c with c to the power log n. Now notice that n to the power log c is actually the same as c to the power log n, right? This is by the property of logarithms, and they are basically the same functions. As they are exactly the same function, they are theta of each other, right? So basically it would be big O, it would be big omega, and it would be theta, right? Now because it is theta, it cannot be little o and it cannot be little omega. And finally we have log n factorial compared with log of n to the power n. Now recall, even in this question, as a hint, one of the results that was presented was log of n factorial is theta of n log n. Now notice that this log of n to the power n is basically n log n from the property of logarithm, and therefore this log of n factorial belongs to theta of log of n to the power n from this relation over here. Okay, so this is going to be theta. Because it is theta, it will be big O and also big omega, and it cannot be little o or little omega. Okay, so as you can see, for solving most of these problems, you just need to know these standard results, and you don't really need to compute limit. You can compute limits, for example we did for this problem, but computing limits for many of these will be too much time consuming, and obviously there is a greater chance of making a mistake in limit computation. So remember these properties. The third question is basically asking us to figure out complexity of several recurrences using master theorem. So essentially we need to figure out the value of a, b, f of n, and n to the power log 2 base b of a for each of these recurrences, and then compare f of n with n to the power log 2 base b of a to determine the complexity from master theorem. Alright, so here this 2 is basically a, this 4 is b, this f of n is basically this constant 1, right? And because a and b are 2 and 4 respectively, n to the power log 2 base b of a is given by n to the power log 2 base 4 of 2, which is basically n to the power half, which is square root n. Now clearly and this square root n grows faster, this square root n grows faster than 1, right, which is f of n. So this is going to be case 1 of the master theorem, which implies that in this case t of n belongs to theta of square root n. Here again we have to figure out the same thing, so let's quickly do this. This a is 2, b is 4, f of n is square root n, n to the power log 2 base b of a is basically n to the power log 2 base 4 of 2, which is again square root n. Now clearly in this case this square root n is the same function as f of n, which is square root n here. So here case 2 of the master theorem applies, which basically means t of n belongs to theta of square root n log n. Moving on to part C, here a is 2, again b is 4, f of n is n in this case, so n to the power log 2 base b of a is given by again square root n. Now comparing these two functions, clearly n, this function f of n grows faster than square root n, right? So this n grows faster than square root of n, so this implies perhaps case 3 of the master theorem, but we still need to check two more things. So first of all, this f of n should be growing polynomially faster, at least polynomially faster than square root of n. So let's check whether that is true, right? So if we do n divided by square root n, we get square root n, which is basically n to the power half, which is of the form n to the power epsilon, right? So this means that f of n grows at least polynomially faster than n to the power log 2 base b of a. So this satisfies the first check. Now let's do one more check, the second check. So we need to check the regularity condition, which basically says that a times f of n by b should be less than equal to c times f of n for some constant c less than 1, right? For c less than 1. Now in this case basically this a times f of n by b is equal to n by 2, right? So this here is n by 2 simply, and so the regularity condition holds for c equal to half. Okay, so therefore case 3 applies. So case 3 applies here, which basically implies that t of n belongs to theta of f of n, which is simply n, right? So this is our answer. All right, here again a is 2, b is 4, and f of n in this case is n square. So n to the power log 2 base b of a is given by again square root n, because b is 4 and a is 2. So obviously square root n grows slower than n square. So it seems like case 3 applies, case 3 of the master theorem, but we still need to check the two conditions. The first condition is that this function f of n should grow polynomially faster than n to the power log 2 base b of a. So let's check that. If you divide n square by root n, you basically get n to the power 2 minus half, and this is clearly of the form n to the power epsilon, which is polynomial growth. So the first condition satisfies. The second condition is that of regularity. So we once again need to check that a times f of n by b should be less than equal to c times f of n for some constant c less than 1. Okay, so in this case this a times f of n by b is basically simply n square divided by 8 right now, and clearly this is going to be smaller than equal to c times f of n for c equal to 1 by 8. Okay, and therefore case 3, the second regularity condition also satisfies, so case 3 applies. Now case 3 implies that t of n basically belongs to theta of f of n, which is simply theta of n square in this case. So this is our answer. Now this is a slightly different recurrence. So here in this case a is equal to 1 because the coefficient here is 1. B is basically 10 by 7, and f of n is n. So n to the power log 2 base b of a is given by n to the power log 2 base 10 by 7 of 1, which is basically n to the power 0, and which is basically 1, right? So clearly 1 grows slower than n. So case 3 seems to apply. Sorry about that. So case 3 seems to apply, but we still have to check the two conditions. So the first condition is that this f of n should be growing polynomially faster than n to the power log 2 base b of a, right? So if we compute this ratio n divided by 1, we get n, which is of the form n to the power epsilon, where in this case epsilon is equal to 1, right? So the first check passes, this is growing polynomially faster. The second check is that of regularity conditions. So a times f of n by b should be less than equal to c times f of n. So for some constant c less than 1. Okay, so let's see whether this is also true. So this is 1 into f of n is simply n, so n divided by b would be 10 by 7, so this 7 goes up, so you get 7n by 10. Now this is less than equal to clearly 7 by 10 times n, so this implies that for c equal to for c equal to 7 by 10, the condition is true, right? So 7 by 10 is less than 1, so the second condition also passes. So this is case 3, which implies that t of n belongs to theta of f of n, which is simply n in this case. The fourth question here is asking us to compute the complexity of these recurrences using the iterative expansion method. So let's get started with this one. Let's substitute n minus 2 in place of n, and figure out what is the value of t of n minus 2. So this basically comes to t of n minus 4 plus n minus 4 plus n minus 2 whole square. Let's substitute this value in here for t of n minus 2 in this expression, right? So we get t of n is equal to t of n minus 4 plus n minus 2 whole square plus n square. Now let's expand for t of n minus 4. So using the same method, we get t of n minus 4 is equal to t of n minus 6 plus n minus 4 whole square. So this is n minus 6. So now let's substitute this value in place of t of n minus 4 in the expression. So we get t of this is equal to t of n minus 6 plus n minus 4 whole square plus n minus uh, n minus 2 square. So let me write it here, n minus 2 whole square plus n square. Okay, so if we go on doing this, we see now, you see there is a pattern emerging here. So you'll see that the ith term would be something like this: t of n minus 2 times I plus summation of k going from 0 to I minus 1 n minus 2k whole square. Okay, this is the ith term. Now let's use this ith term to find a bound, an upper bound on this recurrence. So first of all, for what value of I would this expression inside would this value inside the bracket go down to 0 or 1? So we notice that for I equal to n by 2, this n minus 2i will become 0, right? So 2 times n by 2 is n, so n minus n is 0. So basically this series will go all the way from k equal to 0 to n by 2 minus 1. So let's solve this on the next slide. Have is t of n is equal to t of n minus 2i plus summation k equal to 0 to I minus 1, and here we have n minus 2k whole square. So this term inside the bracket, this will reduce to 0 for I is equal to n by 2. Okay, so basically this recurrence will stop at I is equal to n by 2. So let's substitute this value of I here. So we get t of n is equal to t times n minus 2 times n by 2, which is basically going to be 0, plus summation k is equal to 0 to n by 2 minus 1 n minus 2k whole square. So let's expand this. So we get this becomes t of 0, which is a constant which can be done in constant time, and this would be summation k equal to 0 to n by 2 minus 1 n square minus 4nk plus 4k square. Okay, so this is basically t of 0 plus, let's separate out these terms. So we get summation k is equal to 0 to n by 2 minus 1 n square minus 4n summation k going from 0 to n by 2 minus 1 plus 4 times summation of k square again from 0 to n by 2 minus 1. All right, so let's see what each of these terms actually mean, right? So this term over here, now this is obviously a constant, so we don't need to worry about this. This second term, this is actually simply n square multiplied by n by 2 minus 1, and this is going to be 4 n Actually I think I missed the k here, right? There was a k here. Yes, so this is going to be 4n, and then you are summing k from 0 to n by 2 minus 1, right? So notice that this so basically this term, right, this is similar to that series. Remember, 1 plus 2 plus 3 plus so on up to n by 2, right? So recall that the sum of the first n numbers, natural numbers, is given by n into n plus 1 by 2. Right now in this case the sum is only going up to n by 2 minus 1, so but this is still going to be theta of n square, right? Because n into n plus 1 by 2, if you open this up you get n square, the largest degree, right? So this is theta of n square. Now notice this, so I'm going to directly say here, this is basically some theta of n square, like this, and you're multiplying that by 4n. So basically this becomes theta of n square multiplied by 4n, right? And so this is the second term here, and the third term is basically, notice that this is basically similar to, recall, 1 square plus 2 square plus 3 square plus so on up to n by 2 minus 1 whole square, right? So recall that the sum of this series is given by n into n plus 1 into 2n plus 1 divided by 6, right? So although the summation in this case is only going up to n by 2 minus 1, this is still in terms of n. So if you open this open the summation, I mean the result for this series, you will find that this term should be theta of n cube. Okay, so you see this, all of these terms are theta of n cube. This is going to be n cube, this is already n cube, this is also theta of n cube. So basically our t of n belongs to big O of n cube. This is our result. So we have basically found a bound to each of these terms and derived the overall complexity from that. The next problem is Tn is equal to T of n minus 1 plus log n. Once again, let's start expanding this term. So let's figure out the value of T of n minus 1. So by substituting n minus 1 here in the recurrence, so we get T of n minus 1 is equal to T of n minus 2 plus log of n minus 1, right? So let's substitute this value over here and we get T of n is equal to T of n minus 2 plus log of n minus 1 plus log of n, right? So now let's once again let's try to expand this T of n minus 2 using the same method. So we get T of n minus 2 is equal to T of, by substituting n minus 2 here, we get T of n minus 3 plus log of n minus 2. Okay, so once again substitute this back here in this recurrence, so we get T of n is equal to T of n minus 3 plus log of n minus 2, and then from above we have plus log of n minus 1 plus log of n, right? So if you continue like this, you'll find that the ith term for this expansion would look something like this. So you will have T of n is equal to T of n minus I plus log of so basically we can write the second term as a summation, right? So summation k is equal to 0 to I minus 1 log of n minus k. So this is basically this second term, this can actually be written as log of I minus 1 factorial, right? So this is basically T of n minus I plus log of I minus 1 factorial. Okay, so let's use this term. So let's use this ith term to find a bound on this recurrence. So far we have T of n is equal to T of n minus I plus log of I minus 1 factorial, right? So notice that for I is equal to n, this value inside the bracket will reduce to 0, right, in this recurrence. So let's substitute this value I equal to n, and we get t of n is equal to t of n minus n, which is constant, and minus n is 0, plus log of n minus 1 factorial. Okay, so this is basically simply t of 0 plus log of n minus 1 factorial. Now let's try to find a bound on this. So notice that this is constant, so we don't need to worry about this. And this log of n minus 1 factorial, well, this should be less than equal to log of n factorial. Okay, and log of n factorial is, we know that it is less than equal to log of n to the power n, right? And basically from here you can see that this log of n to the power n is basically theta of n log n. Okay, so basically from here our recurrence t of n also belongs to order of big O of n log n. This is our result. All right, so part C, we can directly do using the master theorem. So I sent out an announcement saying that for only for this part you can use the master theorem. So let's quickly do that here. So once again, the value of a is 4, value of b is 3, and this is our f of n. The value of n to the power log 2 base b of a is given in this case by n to the power log 2 base 3 of 4, and so this is basically n to the power, roughly n to the power 1.26. If you do the math, if you figure out log 2 base 3 of 4, it's around this value. So we need to compare this function with the n log n, right? So it turns out that n to the power 1.26 actually grows faster than n log n. So and that's because you can, so basically if you cancel out n from both sides, this becomes n to the power 0.26, and n to the power any positive constant is always greater than log n. It grows faster than log n for large values of n. So that's why this n to the power 1.26 is faster than, it grows faster than n to the power log n. So from here basically case 1 of the master theorem applies, and this basically implies that t of n should be big O of theta of n to the power log 2 base b of a, which is simply n to the power log 2 base 3 of 4. So this is our answer here. Okay, so once again here is the next recurrence. Let's expand this as usual. So let's substitute n minus 1 here. So we get t of n minus 1 is equal to t of n minus 2 plus 1 upon n minus 1. Now let's substitute this back here in the recurrence. So we get t of n is equal to t of n minus 2 plus 1 upon n minus 1 plus 1 upon n. Now once again let's expand this t of n minus 2 using the same method. So we get t of n minus 2 is equal to t of n minus 3 plus 1 upon n minus 2. Substituting this back here in the recurrence, we get t of n is equal to t of n minus 3 plus 1 upon n minus 2 plus 1 upon n minus 1 plus 1 upon n, right? So you see there is a pattern appearing here. So essentially for the ith term, if you keep doing this, you will find that t of n is equal to t of n minus I plus summation k going from 0 to I minus 1. We have 1 upon n minus k, right? So this is our ith term. Let's continue this on the next slide. So we had t of n is equal to t of n minus I plus summation k equal to 0 to I minus 1 over n minus k. So notice that this recurrence will stop when I is equal to n, right? So for I equal to n, this value goes down to 0. So substituting for I is equal to n, we get t of n is equal to t of n minus n plus summation k is equal to 0 to n minus 1, 1 upon n minus k. So this is t of 0, this is going to be constant. Now what about this series, right? You see this series, if you notice, this is actually this actually looks like this, right? So this series is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus so on up to 1 by n, right? So this is a harmonic series, right? And the sum of the harmonic series is actually O of log n. Okay, so basically this second term is theta of log n or big O of log n, and basically, and from that, this t of n also belongs to big O of log n. The second term basically determines the complexity of our recurrence. So this is the answer. Alright, so that brings us to an end of this discussion. I hope these video solutions were helpful. If you have any questions, something is not clear, please write to me or stop by. Thank you.